So the purpose and objectives of this course, which, as many of you know, was to be delivered, face to face in a training room. But the purpose of this course, I think the key word is really overview. So this is a big topic, vulnerabilities of positioning, navigation and timing. But we do hope today to provide an overview, particularly focusing on raising awareness, helping you to identify and think through the risks that you may experience or be exposed to, and then consider in a very generic way mitigation approaches. So how to rationalize this whole issue and question of the vulnerabilities and securing positioning, navigation and timing systems. Before I go on any further, I do want to recognize the support of the UK Space Agency in supporting the Institute and enabling these webinars to take place, and indeed for all of you to join free of charge. So many thanks to them. Just a little bit more on the schedule of the webinars. So first up is myself. I'm going to talk in a minute to give an introduction, to set the scene, and then Guy will talk about the different types of vulnerability and give some examples. We'll then have a break and then come back with a second webinar. All these links, by the way, are available on our website under the events section. If you haven't got them in an email, just go to the events section and you'll see the links to join these webinars directly. Second one's at 11:45. Dr. Mark Dunville of Nottingham Scientific Limited is going to give us a bit of an overview of the Strike 3 project, where he and a whole team have deployed field detectors. So there's some real hard data that Mark's going to present of what's actually out there in terms of jamming and interference. And then Mike Jones is going to, from Rope Manor, is going to talk about how we can actually locate those threat sources. And then after our virtual lunches on our own around the country and around the world, Tim Frost from Calnex Solutions is going to talk about the T in PNT, so the timing vulnerabilities and mitigations. And then Mike Jones is coming back on to start talking about how do you add resilience. And Mike is going to focus on adding resilience at the receiver and antenna level, so if you like, upstream. And then next week, this is just to keep us on our toes, next week, next Wednesday, the 25th of March, Professor Terry Moore will talk about how you can add resilience through additional sensors. And after that session, if there are questions that we can't address today, we'll try and take those questions live after that session a week today. So that's the overview of what we're going to cover today and next Wednesday. And thank you very much for joining. I'll kick off with the leveler, if you like, with the introduction. So I want to cover why is GPS, GNSS vulnerable, and talk about how you define performance and assess risks, and very generically talk about mitigation approaches. So these are the 4 GNSSs, Global Navigation Satellite Systems. GPS, run by the US. In the center on the left there, GLONASS, run by Russia. And bottom left, Beidou, or you may hear it called Compass. And I'm reliably informed that Beidou in Chinese, or in Mandarin, is North Star. And then on the right-hand side, Galileo, the European system. There's no particular reason, by the way, that Galileo is separate from the other 3. It's just that on that world map that I was able to source, Europe was right in the middle of it, so I put Galileo over there. But these are all global navigation satellite systems. They have global coverage and a network of satellites around the world. There are other satellite systems which are beyond the scope of this presentation. I'm actually doing another webinar next Tuesday, the 24th at 4 p.m. GMT, and I'm going to go into more detail about other satellite navigation systems in that slot. But for now, these are the 4 GNSSs. This is a very busy diagram, but I think it's very helpful. So the question this seeks to answer is, where are these GNSS satellites? And you've probably heard about geostationary orbit, medium Earth orbit, and low Earth orbit. GEO, MEO, and LEO. And you can see these on this chart, and particularly focus on the vertical axis there, the one that says 5 hours, 10 hours, etc. So if we go to the top, geostationary orbit, these are satellites that are 36,000 kilometers above the equator. And Arthur C. Clarke in the 1950s, I think it was, figured out that by placing satellites in that position, they would orbit the Earth exactly every 24 hours. In other words, magically, they actually stay stationary above the equator as they undertake their orbit. And this is a wonderful discovery because it allows us to have fixed antennas on the Earth that will always be pointing at the satellite that we've peaked those antennas up at. So that's why you can collect Sky satellite TV, for example, on a fixed dish, because that dish is pointing at a geostationary satellite above the equator. And that's a very crowded bit of real estate, as you can imagine. So that's 36,000 kilometers, 24-hour orbital period. The GPS satellites and the other GNSS satellites are not geostationary. So they are in what's called medium Earth orbit. And as indicated by this diagram, you can see that the orbits are actually, they're not all the same height above the surface of the Earth. But in round figures, it's 20, 21, 22, 23,000 kilometers. Galileo is slightly further out than GPS, which in turn is slightly further out than Galileo. But they're all in geostationary orbit. The satellites are moving very quickly in relation to the surface of the Earth. In very round figures, you've got about a 12-hour orbital period. GPS is on the money for that. Galileo is a bit longer, GLONASS a bit less. But if you think about 12 hours for an orbit, and the Earth's obviously orbiting at a different frequency, you can imagine that the satellites are moving very quick, several thousand kilometers an hour, I believe, above the surface of the Earth. So all these satellites are moving very quickly, and they're in medium Earth orbit. Very briefly, if I come right in towards the surface of the Earth, you can see it's marked Iridium, Hubble, International Space Station, etc. Yes, so at these orbits, the orbital period is much, much quicker. Maybe of the order of an hour and a half, something like that. I think the Iridium satellites, for example, which are in low Earth orbit, it's a 100-minute orbital period. And the Hubble Space Telescope, International Space Station, you're talking about a few hundred kilometers. I think the International Space Station orbits at about 400 kilometers. So much, much closer into the Earth than the GNSS satellites. So that's where these satellites are. And with somewhere between 24 and 30 satellites in each of those 4 GNSS constellations, a receiver on the surface of the Earth with a clear sky can typically see 7, 8, 9, 10, that order of number of satellites as indicated here. So this is a sky plot from an antenna on the surface of the Earth looking at the GPS satellite constellation. And I think you can see, if you count them up, I think there are 10 satellites visible there. 3 of them are in red because they're very low elevation. So this sky plot has got the 0 elevation around the edge, going up to zenith in the center. So really, you've got 7 satellites available to you, and that's fairly typical from each constellation. So this is a big topic. Going into detail on that's outside the scope here, but just take that away. So you've got 7 satellites to 10 satellites from each of the 4 constellations. So why are they vulnerable? This is well, the first answer to that question is that they're extremely low power by the time they reach the surface of the Earth. So these signals from the satellites, very low power. So here is a spectrum analyzer plot. So this is the spectrum from relatively low frequency on the left, about 10 megahertz, to higher frequency on the right, about 3 gigahertz, of all the different radio signals in the UK. Let's just go through some of them briefly. Number 3, which I think is the highest power, that's actually Tetra, which is emergency services radio. Then the next tranche of high power ones are cellular phones. So I think number 8 is GSM. Number 6 is GSM. There's some LTE 5G in there as well. Number 4 on the left there is at about 480 megahertz is digital TV. And just a bit lower than that, number 2 is digital analog radio. Number 1 is FM radio. So what is it? 88 to 91 FM radio 1, is that right? So that's those are those signals. There's a bit of a cluster on the right at 2.4 gigahertz, number 10. So those are all the different Wi-Fi frequencies. And number 7, you can just about see that, just to the right of center, number 7, that's Iridium. So that's the global handheld phone and data low Earth orbit satellite system, about 1.6 gigahertz. Now just think for a minute how much closer Iridium is to the surface of the Earth than the GPS satellites. And you'll soon realize that, well, where are the GPS satellites? The answer is you can't see them on a plot like this. And the reason is that by the time those signals reach the surface of the Earth, the power level is below what's called the thermal noise floor. So in order to bring those signals out from below the thermal noise floor, you need a GPS receiver. You can't actually see them on a spectrum analyzer. So the key takeaway in this introduction is they're extraordinarily low power signals. It's called spread spectrum techniques are used. They're very low power signals. As an example, if you think about a 1 watt torch, when you were shining that 1 watt torch, the equivalent power level of GPS satellite signals by the time they reach the Earth is you'd have to be 700 miles away from that 1 watt torch, approximately. So very, very low power signals. Another one that I like is a car headlight viewed from Australia in the UK. You know, it's that type of extremely low power that you get from. So that makes them vulnerable to interference. And Mark Dunville will come and talk about that much more in his slot coming up in the second webinar. Another reason the signals are susceptible is that the civil signals are unencrypted and the signal specifications are published. So if you go on to Google and search GPS L1, as I've done here, you'll immediately get all sorts of returns showing you the spectra, the modulation schemes, and information about the navigation data. You can see that bottom left of the screenshot. But that's not all. The detailed information is published, not just by GPS, as shown here, but by all of the GNSS signals. So you can go on the web and Google any of these 3 on the left. The interface specification for GPS, 200 is the L1 and L2 frequency signals. 700, I think, is L5 frequency, and 800, I think I'm right in saying, is the L1C, so the new civil signal for GPS, which is coming up on the GPS 3 satellites. I think another one was launched very recently. Why is this out there? Well, it's absolutely essential to enable receiver designers to build receivers. And then over time, over the history of GPS, test equipment manufacturers started building simulation systems. Guy, who you'll hear from in a minute, is from Spirent, and they design and develop simulation systems. All good stuff. Unfortunately, more recently, particularly, there's been a lot of intentional interference for a whole variety of reasons, which Guy will, go into detail on. But the fact that the signal specification is published and unencrypted and openly available doesn't help. Let's say that. So just to touch on this, Guy again will go into more detail. Here are a range of typical vulnerabilities that you can expect. Some of them are intentional, like spoofing on the left-hand side and intentional interference. Some of them are unintentional, either unintentional interference between some of those signals that I mentioned, for example, or even natural. I mean, multipath signal bounces are a vulnerability of GNSS, and they're natural. Atmosphere on the bottom right is a natural phenomena that we have to take account of. And then there's the human error factor. So, for example, segment errors. And Guy will talk more about those, but generically, spoofing, interference, and cyber attacks are on an upward trend. And the others are just things that we have to deal with and are not particularly going up, in my opinion, but they're certainly out there. So there's a range of vulnerabilities. Right, so my talk within its scope was talking about how do you identify risks. Well, in order to assess the risk, I would suggest you need to have a clear understanding and preferably definition of the needs and the requirements of your system. So before you can assess the risks, think about and define the requirements and the priorities. And then having assessed the risks, you can start to think about the right technology selection and mitigations. So how do you define requirements for a complex system like a navigation, positioning, and timing system? Well, people tend to think about accuracy first. How accurate does it need to be? But just look at these different generic application areas, and you'll immediately see some other key differences that we need to take into account. Is the system safety critical or not? So a mobile phone probably isn't, but a port system or a rail system or an aviation system almost certainly is. What about commercial criticality to your operation? And also there are regulatory factors to take into account. So very, very different user needs. One size most definitely does not fit all. So in starting to think about how to put a requirements definition together, here are some of the approaches that are typically used to define requirements. So there is no one standard, and in many areas there are no standards at all for positioning, navigation, and timing performance definition. But what you see on the screen here is an approach called the required navigation performance definition. And if you want more information on that, if you Google Navipedia, you'll find more information on this. Here are 4 parameters that are extremely helpful in bounding and defining requirements for a positioning, navigation, and timing system. At the top there, accuracy, so the reported position versus the true position. On the left, integrity, which is a measure of trust. It can also be a measure of timeliness of any warnings. On the right-hand side, availability, which is defined as the percentage of time a system is available to provide a position. And at the bottom, continuity, which is defined as the probability that the system performance is maintained at the required accuracy without interruption. So here are 4 parameters. Let's try and bring them to life a little bit. So here you see those parameters very indicatively. So please, any engineers on the call, and I'm sure there are many of you, this is not precise. This is indicative. And yes, it is indicative that there's some conflict between these factors. That's a true factor, but please don't read it as integrity is directly in contract with availability. That's not the case. But just indicatively, here's the likely ranking in a red, orange, green, green being high, red being low, for a simple handheld, old-fashioned hiking receiver that you might use on the hills, just GPS or just GNSS. So accuracy actually can be quite good, particularly if you're in an open sky position. You know, you may hear 5 meters being quoted, even better perhaps with multi-frequency. But there are no guarantees over availability, and certainly there's very rarely any flag that there's a problem. So they're very rarely you can't really trust or know that you can trust what you're reading on your device. And continuity, well, most of the time it'll work, but it may well not. So that's a example of how this could be applied. The good news is there are a whole range of techniques to improve this, and you'll hear about these through the webinars today, and indeed next Wednesday with Terry Moore. But here's a simple example. So there's a technique called RAIM, Receiver Autonomous Integrity Monitoring, which uses some of the satellites you don't need for a position to give you an integrity check. So here you can see you can improve the integrity by using RAIM. It'll give you a flag and or exclude satellites which are suspect from the position calculation. Other technologies have very different performance against these requirements definition parameters. And again, indicatively, here's how a MEMS inertial, a micro inertial system might be characterized. So it's on all the time, very difficult to spoof or jam, but very high drift in accuracy. So while it might be fairly accurate initially, it's open loop cumulative, and Terry will talk more about this next Wednesday. So very poor accuracy. Integrity, well, yes, it doesn't necessarily tell you whether it's good or bad what you're reading, so not great. But if you compare that to what we saw just a minute ago with GPS, you'll see there's some complementarity there. And indeed, if you add the two together, so if you have a system with GPS coupled with inertial, then, and by the way, the real world's not this simple, but you can move to a higher performance system. So I would advocate that defining your performance in this way is extremely helpful. It helps you think about what is important for the system or application that you are working on. And it also allows you to start thinking through the vectors of your risk. This chart, if there's a message from this chart, it's that no single technology element performs well across all of those requirements definition areas. So none of these core technologies on the left would give you 4 greens on that performance framework that I just went through. So therefore, in order to get performance that is going to meet the system needs, the user needs, it's almost always necessary to start thinking about a system-based approach, systems integration, if you like. And actually, it's my personal view that we need to do a lot more systems integration thinking and perhaps be more professional as a industry sector in systems integration thinking. Maybe there's a role for the RAIM there, but no single element's enough. So you've always got to think about assessing the benefits of each element individually against your performance, and then how they'd operate combined. Let me give you an example. So here is a actually quite complex positioning, navigation, and timing system, and one that we're all familiar with. I want to give you an example of how integrating different technology elements together can improve performance. Cell phones are very interesting, in my opinion, from a PNT perspective. They're optimized very strongly on availability, not performance, not accuracy, and not integrity. And let me just run through some examples of that. So here's a couple of screen grabs from my smartphone. If you're wondering, this is in Romania, but it could be anywhere in the world. That's by the by. But you've got a good position from GNSS. This particular smartphone had GPS and GLONASS. You've got good position, slightly better on the right. There's no blue zone of uncertainty. On the left, maybe slightly degraded. So you're getting a little bit of feedback there. Maybe 5 meters in open sky. In this shot here, I've actually moved to a position where GNSS is denied. And that's not very hard. All I did was I walked from my hotel balcony into the concrete room and closed the door. So what you're seeing here is a much wider zone of uncertainty. And this is Wi-Fi positioning. So this is the phone picking up Wi-Fi. Here you've got about 20 to 50 meters of positioning. Yeah, Wi-Fi is a whole nother topic, but it's going to get a lot better with 5G, I think, or in the 5G era. That's the topic of another webinar. So that's Wi-Fi. And then if I turn off Wi-Fi and I turn off Bluetooth, oh dear. Well, here I'm at about a few hundred meters of accuracy, typically 200 to 500 meters. And that's because my phone is giving me a position based on cellular. So this is just base station positioning based on a raw sort of power level from the base station. Again, this will get better with 5G. As 5G technology rolls out, there are all sorts of techniques which can improve the accuracy here, measuring the round trip time rather than just the power level. But at the moment, this is what you're looking at. So you can see that this device's performance has been defined roughly, as you can see on the right. So the most important priority is availability. When my app pings my operating system for a position has to be delivered. It's no good saying, I haven't got a position at the moment. And that has been prioritized above accuracy and above continuity. And I don't know about you, but apart from the little blue zone of uncertainty, my phone doesn't tell me that I've got a suspect position. So just one example of how a device that we all use every day has had the design decisions made based on a very clear view of how the performance is defined against this parameter definition from Navipedia. I suggest you can apply that to any application, and the thinking that through will be extremely helpful then in how do you make the choices that you need to make. Just in a few minutes, I want to touch on and introduce conceptually thinking, what you can do about all of this. And you're going to hear more about this through the webinar, but there is a lot you can do. There's no one answer, but some of the things you can do are pretty straightforward. And if you look at the little indicative diagram with the 4 GNSSs on the left, you can use more than one system. So you can use more than GPS. You can combine different systems together to give you more satellites. That helps to improve performance. They're not necessarily accuracy, but it does help to improve performance. And you can also use multiple frequencies. So that's starting in cell phones and is quite common in other areas as well. And that helps to remove the atmospheric ambiguity and can give you accuracies of about 1 meter rather than about 5 to 10 meters. There are a host of other things you can do. So Mike Jones will touch on antenna mitigations. So there are all sorts of different antenna techniques to really help to improve performance and block out signals you don't want. Differential GPS, I think, will be touched on by Terry Moore next Wednesday. This is a technique whereby you measure the position from a receiver that's at a known surveyed location on the ground. And then indicated in green, bottom left here, you get an error that you can then transmit to a user device nearby. And that user device can then back out those errors. So that's just a conceptual idea, but that's what differential GPS can do for you and deliver much better integrity and an order of magnitude improvement in position. These correction systems, or augmentation systems as they're called, can also be from space. So you may have heard of SBAS, space-based augmentation systems. These are geostationary satellites which transmit corrections for satellite errors, track errors, clock errors, and so on, and also ionospheric corrections over a wide area. And I touched on, I mean, here's just one example of a receiver level technique. I touched on RAIM earlier. So choosing one or more of these different mitigation techniques based on an assessment of your requirement and your risk is a good way to start thinking through the challenges associated with securing, positioning, navigation, and timing systems. If you take that phased approach, I think it will help you to take an informed view. And even if you still need to refer to an expert, like some of the people you're going to hear later on in these webinars, so if you need to refer to an expert, it might help you frame the question or assess their responses. So that's really what I wanted to say as a leveling intro. I hope that was helpful. I will hand over to Guy. There are resources available. If you follow this link on the RIN website, then there are various, we've pulled together different resources that can provide more guidance and more information if you want to dig a bit deeper.